Hey, welcome. Today we're going to be talking through how to draw ray diagrams for concave and convex mirrors. So maybe you need to do this for a physics class, and I'm going to show you exactly what you need to know and the 6 major logical options that you could have for problems for drawing ray diagrams for concave and convex mirrors. So let's go ahead and get to it. First though, I do want to remind you of the law of reflection. And it's real easy. That is just the angle of incidence is equal to the angle of reflection. So this angle, as measured to the normal, is equal to this angle over here. Light behaves in this way, and that's just something you're going to want to keep in the back of your mind as we do this kind of thing. All right, let's take a look at what we mean by a focal point and a focal length. It turns out that if you have parallel rays coming in, and immediately you could say parallel to what? Well, let's create something called an optical axis right here. That'll be our axis that goes right down the middle of the curved mirror. So this is a spherical curved mirror right here. So it's a section of a sphere, usually is how it's done. And if these parallel rays come in, these red rays right here, they come in, something special is going to happen with this. They will come in and basically hit at a certain point. They will all strike more or less or intersect at the same points. There is a little bit of caveat in this, and we will correct for that later, and I'll talk about that later. But let's just say for now that they all perfectly cross right at the focal points. This down here is going to be called the focal length. Usually measured in centimeters, it's going to be the distance between the focal points and the curved mirror itself. Alright, well let's make that into our first rule. There are going to be 3 rules that we need to master for understanding how to draw ray diagrams. And the first one is that if the rays come in parallel to the optical axis, the rays will reflect through the focal point. We just saw how that works for a concave mirror example. Let's think about how that would work for a convex mirror example. So over here on the right side, you don't have a focal point or a focal length on this side of the mirror because this is the curved side. You can think of the focal point as being half the distance to the center of this mirror if it were a complete circle or a complete sphere. So what side is the focal point going to be on? Well, the focal point is going to be on the right side. And that's where we're going to trace these back. So like this ray coming in right here, it's going to bounce off as if it had gone through the focal points. This ray right here is going to come in and bounce off as if it had gone through the focal point as well. And you can think about these rays tracing back and sort of intersecting at this point that we're going to call the focal point. And so that's our first rule. I'm going to show you how to apply all 3 of these rules, but let's talk about the second rule first. Oh, before I continue, there is one thing. We're going to have a positive F value if you have converging light for a mirror on the front side of the mirror. The way I think of this is just think what we would expect to have is just the mirror converge rays on the front side of the mirror, and that'll be considered to be positive. And if it converges behind the mirror, you could say that that means it's diverging light, and that's going to be on the back side of the mirror. All right, let's take a look at our second rule and see how this works. So our second rule is if a ray comes in through the focal point, it will reflect parallel to the optical axis. So think about what these arrows would look like after they interact with the mirror. And remember, these are all following the law of reflection still. So imagine what these reflected rays would look like right now, please. Alright, so they're going to bounce straight back like this. They're going to be parallel to the optical axis. So that's how it would look for a concave mirror example. Let's take a look and see how it would look for a convex mirror example. So if we have rays coming in as if they were going to go through the focal point. Now the focal point is on the right side. It's not on the left side. So they're going to be coming in as if they were going to go through the focal points. How are they going to bounce back? What's our second rule say? Well, it says that they're going to bounce back parallel to the optical axis, so I'm going to show you what that looks like right now. So those reflected rays will follow the law of reflection, but also follow this rule right here. And let's take a look at our third rule as well. So our third rule is pretty straightforward. Our third rule is that if a ray comes in through the center of curvature, this would be like in the very center of a spherical mirror if this was a big spherical mirror. Notice this is a little bit wacky, so imagine this is more spherical shaped, and this is just a section of that sphere, so to speak. So if the rays come in through the center of curvature, they're just going to bounce straight back. If you think about it, it should be bouncing straight back because it's going to be hitting this at a right angle to the surface. Now this surface isn't perfect. Imagine this is going to hit perpendicular and bounce straight back. That's what's happening here for the third rule. And let me show you what that looks like for the convex mirror example. So if these rays bounce in as if they were going to go through the center of curvature, the very center of the spherical mirror, then they would bounce straight back. So those are our 3 rules. What I want to do is just finish up this quick screencast, and I'm going to make a part 2 for this where I show you how to apply this in the 6 logical options that you can face as problems for your physics class. So hopefully this has been helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.